Okay, welcome back. Let's try reading Chapter 2 of Functional Programming in Lean. Chapter 2, Hello World. While Lean has been designed to have a rich interactive environment in which programmers can get quite a lot of feedback from the language without leaving the confines of their text editor, it is also a language in which real programs can be written. This means that it also has a batch mode compiler, a build system, a package manager, and all the other tools that are necessary for writing programs. While the previous chapter presented the basics of functional programming in Lean, this chapter explains how to start a programming project, compile it, and run the result. Programs that run and interact with their environment, for example by reading input from standard input or creating files, are difficult to reconcile with the understanding of computation as the evaluation of mathematical expressions. In addition to a description of the Lean build tools, this chapter also provides a way to think about functional programs that interact with the world. 2.1 Running a program. The simplest way to run a Lean program is to use the --run option to the Lean executable. Create a file called hello.lean and enter the following contents. Okay, let's try that. Then from the command line run lean-run hello.lean. Okay, it works, nice. Anatomy of a greeting. When lean is invoked with the --run option, it invokes the program's main definition. In programs that do not take command line arguments, main should have type IO unit. This means that main is not a function, because there are no arrows in its type. Instead of being a function that has side effects, main consists of a description of effects to be carried out. As discussed in the preceding chapter, unit is the simplest inductive type. It has a single constructor called unit that takes no arguments. Languages in the C tradition have a notion of a void function that does not return any value at all. In Lean, all functions take an argument and return a value, and the lack of interesting arguments or return values can be signaled by using the unit type instead. If bool represents a single bit of information, unit represents 0 bits of information. IO alpha is the type of a program that, when executed, will either throw an exception or return a value of type alpha. So we don't get, I guess, a separate notion of which exception the programs can throw. But I think it's actually the same also in Haskell's IO monad. During execution, this program may have side effects. These programs are referred to as IO actions. Lean distinguishes between evaluation of expressions, which strictly adheres to the mathematical model of substitution of values for variables and reduction of sub-expressions without side effects, and execution of IO actions, which rely on an external system to interact with the world. IO.println is a function from strings to IO actions that, when executed, write the given string to the standard output. Because this action doesn't read any interesting information from the environment in the process of emitting the string, IO.println has type string to IO unit. If it did return something interesting, then that would be indicated by the IO action having a type other than unit. Functional programming versus effects. Lean's model of computation is based on the evaluation of mathematical expressions, in which variables are given exactly one value that does not change over time. The result of evaluating an expression does not change, and evaluating the same expression again will always yield the same result. On the other hand, useful programs must interact with the world. A program that performs neither input nor output can't ask a user for data, create files on disk, or open network connections. Lean is written in itself, and the Lean compiler certainly reads files, creates files, and interacts with text editors. How can a language in which the same expression always yields the same result support programs that read files from disk when the contents of these files might change over time? This apparent contradiction can be resolved by thinking a bit differently about side effects. Imagine a cafe that sells coffee and sandwiches. This cafe has two employees, a cook who fulfills orders and a worker at the counter who interacts with customers and places order slips. The cook is a surly person who really prefers not to have any contact with the world outside, but who is very good at consistently delivering the food and drinks that the cafe is known for. In order to do this, however, the cook needs peace and quiet and can't be disturbed with conversation. The counter worker is friendly but completely incompetent in the kitchen. Customers interact with the counter worker who delegates all actual cooking to the cook. If the cook has a question for a customer, such as clarifying an allergy, They send a little note to the counter worker who interacts with the customer and passes a note back to the cook with the result. In this analogy, the cook is the lean language. When provided with an order, the cook faithfully and consistently delivers what is requested. The counter worker is the surrounding runtime system that interacts with the world and can accept payments, dispense food, and have conversations with customers. Working together, the two employees serve all the functions of the restaurant, but their responsibilities are divided, with each performing the task that they're best at. Just as keeping customers away allows the cook to focus on making truly excellent coffee and sandwiches, Lean's lack of side effects allows programs to be used as part of formal mathematical proofs. It also helps programmers understand the parts of the program in isolation from each other, because there are no hidden state changes that create subtle coupling between components. The cook's nodes represent I/O actions that are produced by evaluating Lean expressions, and the counter worker's replies are the values that are passed back from the effects. The RTS executes these actions, delegating to the user's Lean code to carry out computations. Primitives in the runtime system written in C implement all the basic effects. When running a program, the RTS invokes the main action, which returns the new I/O actions to the RTS for execution. From the internal perspective of Lean, programs are free of side effects, and I/O actions are just descriptions of tasks to be carried out. From the external perspective of the program's user, there is a layer of side effects that creates an interface to the program's core logic. Yeah, I think this is a pattern that's actually, from what I've heard, common in functional programming, called functional core imperative shell. So we have the core that is essentially a pure, just consists of pure functions, and then we have a small shell around those functions, essentially, that are the functions that actually produce I/O actions and interact with the real world. And obviously it's quite nice to have a lot of pure functions, because you know that they cannot do shady stuff like access some global state, or that they always just behave the same way when they're called with the same arguments, which is obviously not true for a C function. Real-world functional programming. The other useful way to think about side effects in Lean is by considering I/O actions to be functions that take the entire world as an argument and return a value paired with a new world. In this case, reading a line of text from standard input is a pure function, because a different world is provided as an argument each time. Writing a line of text to standard output is a pure function, because the world that the function returns is different from the one that it began with. Programs do need to be careful to never reuse the world, nor to fail to return a new world. This would amount to time travel or the end of the world after all. Careful abstraction boundaries can make this style of programming safe. If every I/O action accepts one world and returns a new one, and they can only be combined with tools that preserve this invariant, then the problem cannot occur. This model cannot be implemented. After all, the entire universe cannot be turned into a Lean value and placed into memory. However, it is possible to implement a variation of this model with an abstract token that stands for the world. When the program is started, it is provided with a world token. This token is then passed on to the I/O primitives, and their return tokens are similarly passed to the next step. At the end of the program, the token is returned to the operating system. This model of side effects is a good description of how I/O actions as descriptions of tasks to be carried out by the RTS are represented internally in Lean. The actual functions that transform the real world are behind an abstraction barrier. But programs typically consist of a sequence of effects rather than just one. To enable programs to use multiple effects, there is a sub-language of Lean called do notation that allows these primitive I/O actions to be safely composed into a larger useful program, combining I/O actions. Most useful programs accept input in addition to producing output. Furthermore, they may take decisions based on input, using the input data as part of a computation. The following program, called hello_name.lean, asks the user for their name and then greets them. Okay, let's try this out. Okay, it works. So I guess we are getting a reference to standard input and to standard output, and then writing the question to standard output and getting a line from standard input, and we drop all white space from the right hand side, I guess. and then we print this interpolated string containing the name back to the output. So if I put whitespace before and after the name, yeah, somehow they only drop the right hand side whitespace. I guess maybe this is to get rid of the return character. Yeah, otherwise it gives us the carriage return or the new line character as part of the string. In this program, the main action consists of a do block. This block contains a sequence of statements, which can be both local variables introduced using let and actions that are to be executed. Just as SQL can be thought of a special purpose language for interacting with databases, the do notation can be thought of a special purpose sublanguage within Lean that is dedicated to modeling imperative programs. I/O actions that are built with do blocks are executed by returning the statements in order. This program can be run in the same manner as the prior program. If the user responds with David, a session of interaction with the program reads, yeah, that's just what we saw earlier. The type signature line is just like the one of hello.lean. Yeah, main is just IO of unit. The only difference is that it ends with the keyword do, which initiates a sequence of commands. Each indented line following the keyword do is part of the same sequence of commands. The first two lines, which are getting standard input and standard output, retrieve stdin and stdout handles by executing the library actions io.getStdin and io.getStdout respectively. In a do block, let has a slightly different meaning than in an ordinary expression. Ordinarily, the local definition in a let can be used in just one expression, which immediately follows the local definition. In a do block, local bindings introduced by let are available in all statements in the remainder of the do block, rather than just the next one. Additionally, let typically connects the name being defined to its definition using : while some let bindings in do notation use a left arrow, either a Unicode arrow or smaller than minus instead. Using an arrow means that the value of the expression is an IO action that should be executed, with the result of the action saved in the local variable. Yeah, so this is just gonna be, I guess, the bind operation of the underlying IO monad, just a syntactic sugar for that, but I think we will probably see that in the chapter on monads. In other words, if the expression to the right of the arrow has type IO alpha, then the variable has type alpha in the remainder of the do block. io.getStdin and io.getStdout are IO actions in order to allow std and stout to be locally overwritten by a program, which can be convenient. If they were global variables as in C, then there would be no meaningful way to override them, but IO actions can return different values each time they are executed. The next part of the do block is responsible for asking the user for their name. Yeah, that seems pretty clear. The first line writes the question to stdout, the second line requests input from stdin, and the third line removes the trailing new line, plus any other trailing white space from the input line. The definition of name uses : rather than an arrow, because string.dropWrite while is an ordinary function on strings rather than an IO action. Yeah, here we have an arrow, here we have : Finally, the last line in the program is stdout.put strln and then the interpolated string that uses the string interpolation syntax that we have already seen previously. Step by step. A do block can be executed one line at a time. Start with the program from the prior section. Standard IO. The first line is let stdin arrow io.getStdin, while the remainder is the remainder of the program. To execute a let statement that uses an arrow, start by evaluating the expression to the right of the arrow, in this case io.getStdin. Because this expression is just a variable, its value is looked up. The resulting value is a built-in primitive IO action. The next step is to execute this IO action, resulting in a new value that represents the standard input stream, which has type io.fs.stream. Standard input is then associated with the name to the left of the arrow, here stdin, for the remainder of the do block. Executing the second line, let stdout arrow io.getStdout proceeds similarly. Yeah. Asking a question. Now that stdin and stdout have been found, the remainder of the block consists of a question and answer. The first statement in the block stdout.put strln and then the question consists of an expression. To execute an expression, it is first evaluated. In this case, io.fs.stream.put strln has type io.fs.stream to string to io of unit. This means that it is a function that accepts a stream and a string, returning an io action. The expression uses accessor notation for a function call. Yeah, so we already saw this, that basically we can use this sort of dot notation to supply the first argument to a function, which means we should be able to rewrite it like this. Let's try it. Yep, it works. So literally it's just syntactic, yeah, this first line is just syntactic sugar for basically this. This function is applied to two arguments, the standard output stream and a string. The value of the expression is an IO action that will write the string and the new line character to the output stream. Having found this value, the next step is to execute it, which causes the string and new line to actually be written to stdout. Statements that consist only of expressions do not introduce any new variables. The next statement in the block is let input arrow stdin.getLine, where io.fs.stream.getLine has type io.fs.stream to io of string, which means that it is a function from a stream to an io action that will return a string. Once again, this is an example of accessor notation. This IO action is executed and the program waits until the user has typed a complete line of input. Assume the user writes David. The resulting line David and the new line character is associated with input, where the escape sequence \n denotes the new line character. The line let name equals input.drop right while char.isWhitespace is a let statement. Unlike the other let statements in this program, it uses equal instead of the left arrow. This means that the expression will be evaluated, but the resulting value need not be an IO action and will not be executed. In this case, string.dropWriteWhile takes a string and a predicate over characters and returns a new string from which all the characters at the end of the string that satisfy the predicate have been removed. Yeah, we have an example that's removing the trailing exclamation marks. Yeah, and we also see this sort of syntax for defining lambda expressions that we had seen previously, which uses the center dot like as a placeholder. I think this should be exactly the same as writing it like this, just like a shortcut. Yeah, and obviously we can supply any function here. For example, removing alphanumeric characters. Yeah, and we are removing the right-hand whitespace of David and then associating it with the variable name for the rest of the block. Greeting the user. All that remains to be executed is the do block in a single statement. Yeah, put string line and an interpolated string which contains the name. The string argument to put string line is constructed via string interpolation, yielding the string hello David. Because this statement is an expression, it is evaluated to yield an IO action that will print the string with a new line to standard output. Once the expression has been evaluated, the resulting IO action is executed, resulting in the greeting. IO actions as values. In the above description, it can be difficult to see why the distinction between evaluating expressions and executing IO actions is necessary. After all, each action is executed immediately after it is produced. Why not simply carry out the effects during evaluation as it is done in other languages? The answer is twofold. First off, separating evaluation from execution means that programs must be explicit about which functions can have side effects, because the parts of the program that do not have effects are much more amenable to mathematical reasoning, whether in the heads of programmers or using Lean's facility for formal proofs. This separation can make it easier to avoid bugs. Secondly, not all IO actions need to be executed at the time that they come into existence. The ability to mention an action without carrying it out allows ordinary functions to be used as control structures. For example, the function twice takes an IO action as its argument, returning a new action that will execute the argument action twice. Yeah, that works. I wonder if we can desugar this to write it without do notation. Like if I rewrite it like this, that appears to not work. So I was just missing the space here, I guess. Yeah, now it works. So the do notation just in this case desugars to this call of the bind method. This can be generalized to a version that runs the underlying actions any number of times. Yeah, for example, you can just run it 3 times. And how it works is, I guess, it pattern matches on the input, and if it's 0, it just gives a no-op IO action, and if it's n+1, then we do the action and do the remaining n actions. I wonder if the indentation here is required. No, I guess not. Still works. In the base case for nut.0, the result is pure of unit. The function pure creates an IO action that has no side effects, but returns pure's argument, which in this case is the constructor for unit. As an action that does nothing and returns nothing interesting, pure of unit is at the same time utterly boring and very useful. In the recursive step, a do block is used to create an action that first executes action and then executes the result of the recursive call. Executing #eval n times io.println hello and 3 causes the following output, 3 times hello. In addition to using functions as control structures, the fact that IO actions are first-class values means that they can be saved in data structures for later execution. For instance, the function countdown takes a natural number and returns a list of unexecuted IO actions, 1 for each natural number. This function has no side effects and does not print anything. For example, it can be applied to an argument and the length of the resulting list of actions can be checked. Okay. Yeah, so this is cons for constructing the list, and yeah. But what if we try to evaluate from 5 itself? Then it says that it's not printable. Yeah, but for example, if we do this, we can, I guess, evaluate the first element in the list, which is then 5. The function run actions takes a list of actions and constructs a single action that runs them all in order. Try this, and yeah, that definitely works. And again, we're here just pattern matching on the list and yeah, running the action and then run the rest of the actions. And the empty list yields a no-op action. The structure is essentially the same as that of n times, except instead of having one action that is executed for each nut.suck, the action under each list.cons is to be executed. Similarly, run actions does not itself run the actions, it creates a new action that will run them, and that action must be placed in a position where it will be executed as part of main. Yeah, or I guess with #eval. Running this program results in the following output. Yeah. Okay, let's see the evaluation steps. So I guess since Lean has a strict evaluation order, it will first completely expand this list and then only then start executing. I guess in a lazy language like Haskell would be more like in a lockstep fashion, like produce the first action and then maybe execute it, and maybe only then the next action is gonna be like even begin to be constructed. The resulting IO action is a do block. Each step of the do block is then executed one at a time, yielding the expected output. The final step, pure of unit, does not have any effects, and it is only present because the definition of run action needs a base case. Exercise. Step through the execution of the following program on a piece of paper. While stepping through the program's execution, identify when an expression is being evaluated and when an IO action is being executed. When executing an IO action results in a side effect, write it down. After doing this, run the program with Lean and double check that your predictions about the side effects were correct. I don't think we need to write it down on a piece of paper, but I think we can see that here it's using the := syntax, so we are literally just assigning the value to this variable. We're not executing it. For that we would need the arrow syntax. So it's going to print first bonjour and then hello. Let's try it out. Yeah, and actually I think if we would use the arrow syntax here, and then like this for example, then we would print first hello and then bonjour. Yeah, seems straightforward enough. Starting a project. As a program written in Lean becomes more serious, an ahead-of-time compiler-based workflow that results in an executable becomes more attractive. Like other languages, Lean has tools for building multiple file packages and managing dependencies. The standard Lean build tool is called Lake, short for Lean Make. Lake is typically configured using a TOML file that declaratively specifies dependencies and describes what is to be built. For advanced use cases, Lake can also be configured in Lean itself. First steps. To get started with a project that uses Lake, use the command lake new greeting in a directory that does not already contain a file or directory called greeting. This creates a directory called greeting that contains the following files. Main.lean, the file in which the Lean compiler will look for the main action. Greeting.lean and greeting/basic.lean are scaffolding of a support library for the program. Lakefile.toml contains the configuration that Lake needs to build the application. Lean toolchain contains an identifier for the specific version of Lean that is used for the project. Additionally, Lake new initializes the project as a Git repository and configures its .gitignore file to ignore intermediate build products. Typically, the majority of the application logic will be in a collection of libraries for the program, while main.lean will contain a small wrapper around these pieces that does things like parsing command lines and executing the central application logic. To create a project in an already existing directory, run lake init instead of lake new. By default, the library file greeting/basic.lean contains a single definition. The library file greeting.lean imports greeting/basic.lean. Yeah, this means that everything defined in greeting/basic.lean is also available to files that import greetings.lean. Okay, so basically we are like re-exporting the definitions from basic by importing them in this greeting.lean file. So I think this is similar to, for example, in Rust, where you can have like a module and then pub use, like the normal way to import something would be with use, but if you write pub use, it then gets kind of like re-exported. So for example, you can call the bar function that usually you would have to write cooks : foo : bar, but since it's re-exported here, you can just use cooks : bar. And I guess this serves a similar purpose here. The executable source main.lean contains import greeting, def main io of unit, and then it prints the hello variable. Because main.lean imports greetings.lean and greetings.lean imports greeting/basic.lean, the definition of hello is available in main. To build the package, run the command lake build. After a number of build commands scroll by, the resulting binary has been placed in .lake/build/bin. Then we can execute it. And I guess you can also execute it with lake exe. Let's try lake init. This created a main.lean and this is giving me an error. Okay, lake build. And we get a kind of huge executable that is 8.2 megabytes. I wonder if it's like Rust where you have to do something like -- release. Apparently not. Yeah, I wonder if it's just that big because it like contains a bunch of debug stuff, or if it really is, just that big. Okay, so just links to a bunch of standard C libraries mostly, I guess. And we also get this lake manifest file that they didn't really mention. Let's try to get syntax highlighting for TOML. Okay, here we are getting a library and an executable, and also a readme. Lake files. A lakefile.toml describes a package which is a coherent collection of Lean code for distribution, analogous to an npm or NuGet package or a Rust crate. A package may contain any number of libraries or executables. The documentation for Lake describes the following options in a Lake configuration. The generated lakefile.toml contains the following. This initial Lake configuration consists of 3 items: package setting, library, and an executable. Each lake configuration file will contain exactly one package, but any number of dependencies, libraries, or executables. By convention, package and executable names begin with a lowercase letter, while libraries begin with an uppercase letter. Yeah. Dependencies are declarations of other Lean packages, either locally or from remote Git repositories. The items in the lake configuration file allow things like source file locations, module hierarchies, and compiler flags to be configured. Generally speaking, however, the defaults are reasonable. Lake configuration files written in the Lean format may additionally contain external libraries, which are libraries not written in Lean to be statically linked with the resulting executable. Custom targets, which are build targets that don't naturally fit into the library executable taxonomy, and scripts, which are essentially I/O actions similar to main, but that additionally have access to metadata about the package configuration. Yeah. Libraries, executables, and custom targets are called targets. By default, Lake build builds those targets that are specified in the default targets list. To build a target that is not a default target, specify the target's name as an argument after Lake build. Libraries and imports. A Lean library consists of a hierarchically organized collection of source files from which names can be imported, called modules. By default, a library has a single root file that matches its name. In this case, the root file for the library greeting is greeting.lean. The first line of main.lean, which is import greeting, makes the contents of greeting.lean available in main.lean. Additional module files may be added to the library by creating a directory called greeting and placing them inside. These names can be imported by replacing the directory separator with a dot, for instance, creating the file greeting/smile.lean with the contents expression.happy of type string is a big smile, means that main.lean can use the definition as follows. Where we import greeting.smile, we open the namespace expression, and then we can use this variable happy that's inside of that namespace. The module name hierarchy is decoupled from the namespace hierarchy. In Lean, modules are units of code distribution, while namespaces are units of code organization. Okay, interesting. That is, names defined in a module greetings.smile are not automatically in a corresponding namespace greetings.smile. In particular, happy is in the expression namespace. Modules may place names into any namespace they like, and the code that imports them may open the namespace or not. Import is used to make the contents of a source file available, while open makes the names from a namespace available in the current context without prefixes. The line open expression makes the name expression.happy accessible as happy in main. Namespaces may also be opened selectively, making only some of their names available without explicit prefixes. This is done by writing the desired names in parentheses. For example, nat.toFloat converts a natural number to a float. It can be made available as toFloat using open nat parentheses toFloat. Worked example: cat. The standard Unix utility cat takes a number of command line options followed by 0 or more input files. If no files are provided, or if one of them is a dash, then it takes the standard input as the corresponding input instead of reading a file. The contents of the input are written one after the other to the standard output. If a specified input file does not exist, this is noted on standard error, but cat continues concatenating the remaining inputs. A non-zero exit code is returned if any of the input files do not exist. This section describes a simplified version of cat called feline. Unlike commonly used versions of cat, feline has no command line options for features such as numbering lines, indicating non-printing characters, or displaying help text. Furthermore, it cannot read more than once from standard input that's associated with a terminal device. To get the most benefit from this section, follow along yourself. It's okay to copy-paste the code examples, but it's even better to type them in by hand. This makes it easier to learn the mechanical process of typing code, recovering from mistakes, and interpreting feedback from the compiler. Getting started. The first step in implementing feline is to create a package and decide how to organize the code. In this case, because the program is so simple, all the code will be placed in main.lean. The first step is to run lake new feline. Edit the lake file to remove the library and delete the generated library code and the reference to it from main.lean. Once this has been done, lakefile.toml should contain, let's try it. Okay, so we don't need the library, which means we can also delete this. We also don't need this, and okay, works. Alternatively, running lake new feline exe instructs lake to use a template that does not include a library section, making it unnecessary to edit the file. Ensure that the code can be built by running lake build. Concatenating streams. Now that the basic skeleton of the program has been built, it's time to actually enter the code. Proper implementation of cat can be used with infinite I/O streams such as def random, which means that it can't read its input into memory before outputting it. Furthermore, it should not work one character at a time, as this leads to frustratingly slow performance. Instead, it's better to read contiguous blocks of data all at once, directing the data to the standard output one block at a time. The first step is to decide how big of a block to read. For the sake of simplicity, this implementation uses a conservative 20 kilobyte block. U size is analogous to size T in C. It's an unsigned integer that is big enough to represent all valid array sizes. Streams. The main work of feline is done by dump, which reads input one block at a time, dumping the result to standard output until the end of the input has been reached. The end of the input is indicated by read, returning an empty byte array. Okay, so now we have, I guess, the answer to how to create a function that's not total by just using the partial keyword. And we get a stream and we return IO of unit, and we're reading a buff size portion of the stream, and if it's not empty we write it to the output and dump the rest of the stream. And I guess this is tail recursive, so it should use a constant amount of stack space even though it's a recursive function. The dump function is declared partial because it calls itself recursively on input that is not immediately smaller than an argument. When a function is declared to be partial, Lean does not require a proof that it terminates. On the other hand, partial functions are also much less amenable to proofs of correctness, because allowing infinite loops in Lean's logic would make it unsound. However, there is no way to prove that dump terminates, because infinite input, such as def random, would mean that it does not in fact terminate. In cases like this, there is no alternative to declaring the function partial. The type io.fs.stream represents a POSIX stream. Behind the scenes, it is represented as a structure that has one field for each POSIX stream operation. Each operation is represented as an IO action that provides the corresponding operation. The type base IO is a variant of IO that rules out runtime errors. The Lean compiler contains IO actions such as io.getStdout, which is called in dump, to get streams that represent standard input, standard output, and standard error. These are IO actions rather than ordinary definitions because Lean allows these standard POSIX streams to be replaced in the process, which makes it easier to do things like capturing the output from a program into a string by writing a custom io.fs.stream. The control flow in dump is essentially a while loop. When dump is called, if the stream has reached the end of the file, pure of unit terminates the function by returning the constructor for unit. If the stream has not yet reached the end of the file, one block is read and its contents are written to stdout, after which dump calls itself directly. The recursive call continues until stream.read returns an empty byte array which indicates the end of the file. When an if expression occurs as a statement in a do, as in dump, each branch of the if is implicitly provided with a do. In other words, the sequence of steps following the else are treated as a sequence of IO actions to be executed, just as if they had a do at the beginning. Names introduced with let in the branches of if are visible only in their own branches and are not in scope outside of the if. There is no danger of running out of stack space while calling dump because the recursive call happens as the very last step in a function and its result is returned directly rather than being manipulated or computed with. This kind of recursion is called tail recursion and it is described in more detail later in this book. Because the compiled code does not need to retain any state, the Lean compiler can compile the recursive call to a jump. Yeah, so the way a tail recursive function like this ends up being compiled is like literally the same way as a loop would be compiled in an imperative language. If feline only redirected the standard input to standard output, then dump would be sufficient. However, it also needs to be able to open files that are provided as command line arguments and emit their contents. When its argument is the name of a file that exists, filestream returns a stream that reads the file's contents. When the argument is not a file, filestream emits an error and returns none. Let's see. We're checking if the path exists. If it doesn't exist, then we print an error and return none. Otherwise, we get a io.fs.handle for the file name and open it as read only. Yeah, I mean, so obviously technically this is a race condition because it could be that that the file exists, then the OS scheduler schedules another process that deletes the file, and then we try to create this handle. So maybe not the way to do it in a real world program, but I mean, for this example, it's obviously okay. Opening a file as a stream takes two steps. First, a file handle is created by opening the file in read mode. A Lean file handle tracks an underlying file descriptor. When there are no references to the file handle value, a finalizer closes the file descriptor. Second, the file handle is given the same interface as a POSIX stream using io.fs.stream.offHandle, which fills each field of the stream structure with the corresponding IO action that works on file handles. Handling input. The main loop of feline is another tail recursive function called process. In order to return a non-zero exit code, if any of the inputs could not be read, process takes an argument exit code that represents the current exit code for the whole program. Additionally, it takes a list of input files to be processed. Okay, so essentially this function is a single do block and contains a match statement that matches the arguments list. Well, if there are no arguments, we just return the exit code. For a minus, we need to open stdin, and well, if it's a file name, then we call our file stream function, and I'm a bit confused by this, but I guess in this case this will invoke the constructor of file path. I mean, this sort of angle bracket syntax, I guess, in Lean, as we saw, can be used to invoke a constructor. Then we check if the stream is none. If it is none, we use 1 as the exit code, but we still continue processing the rest of the args. Otherwise, we dump the stream and we continue processing. Yeah. Just as with if, each branch of a match that is used as a statement in a do is implicitly provided with its own do. There are three possibilities. One is that no more files remain to be processed, in which case process returns the error code unchanged. Another is that the specified file name is a dash, in which case process dumps the contents of standard input and then processes the remaining file names. The final possibility is that an actual file name was specified. In this case, file stream is used to attempt to open the file as a POSIX stream. Its argument is encased in angle brackets because file path is a single field constructor that contains a string. If the file could not be opened, it is skipped, and the recursive call to process sets the exit code to 1. If it could, then it is dumped, and the recursive call to process leaves the exit code unchanged. Process does not need to be marked partial because it is structurally recursive. Each recursive call is provided with the tail of the input list, and all Lean lists are finite. Thus, process does not introduce any non-termination. Main. The final step is to write the main action. Unlike prior examples, main in feline is a function. In Lean, main can have one of three types. Either IO unit corresponds to a program that cannot read their command line arguments and always indicates success with an exit code of 0. and main, if it is IO of uint32, corresponds to an int main void in C for programs without arguments that return exit codes. And main of type from list of string to IO of uint32 corresponds to int main int arg count and char pointer arg vector in C for programs that take arguments and signal success or failure. If no arguments were provided, feline should read from standard input as if it were called with a single dash argument. Otherwise, the arguments should be processed one after the other. Yeah, let's do this. Yeah, empty list is like supplying a single dash, and otherwise we just pass on the args list. What's weird is that I have to somehow close standard input twice, so I'm typing something, I press Ctrl D to close standard input, and then it outputs it, and somehow I have to press Ctrl D again to get out. In normal cut, it's just like ASDF, it's echoed right away after a new line, then I press Ctrl D to close standard input, and we are out. So don't really get why we need to close it twice here. Meow. To check whether feline works, the first step is to build it with lake build. First off, when called without arguments, it should emit what it receives from standard input. Yeah, let's check it. That's because of how ZSH treats the exclamation mark. Yeah, that appears to be working. Secondly, when called with files as arguments, it should print them if the file test1.txt contains some text and test2.txt contains some other text, then we can concatenate them. Finally, the dash argument should be handled appropriately. Yeah, so let's try. Yeah, we get the lake file followed by our dashes followed by the lake manifest, but what happens if we try to open standard input several times? It just does nothing, I guess, and also doesn't return an error. Okay, and if the file is not found, we get an error code. Exercise. Extend feline with support for usage information. The extended version should accept a command line argument -help that causes documentation about the available command line options to be written to standard output. I mean, let's see if we have a single... I mean, this is not maybe a very good way to do it in general, but if there's only a single option available, then we can just do, I guess, something like this. I guess we first need to get... Yeah, let's try this with some AI slop description. Maybe I should actually get into the habit of using the Unicode arrows. Wonder if there's a better way to type it than \left arrow. Like, maybe like this. Yeah. Okay. Yeah, that works. And I mean, the way I implemented it now, if I put it like this, then it will interpret -help as a file. Yeah, but anyway, it works. Additional conveniences. Nested actions. Many of the functions in feline exhibit a repetitive pattern in which an IO action's result is given a name and then used immediately and only once. For instance, in dump. Yeah, we have this buffer, but I guess the buffer is used twice, but here std out, for example, is only used once. Similarly, file stream contains the following snippet. File exists, and then we're using it. When Lean is compiling a do block, expressions that consists of a left arrow immediately under parentheses are lifted to the nearest enclosing do, and their results are bound to a unique name. This unique name replaces the origin of the expression. This means that dump can also be written as follows. Yeah, I mean, honestly, I don't know if this is better because this syntax looks a bit weird when used like that, but yeah, we saved one line, I guess. This version of dump avoids introducing names that are used only once, which can greatly simplify a program. IO actions that Lean lifts from a nested expression context are called nested actions. File stream can be simplified using the same technique. Yeah, we call path exists here using a nested action, and we get std error using a nested action. In this case, the local name of handle could also have been eliminated using nested actions, but the resulting expression would have been long and complicated. Even though it's often good style to use nested actions, it can still sometimes be helpful to name intermediate results. It is important to remember, however, that nested actions are only a shorter notation for I/O actions that occur in a surrounding do block. The side effects that are involved in executing them still occur in the same order, and execution of side effects is not interspersed with the evaluation of expressions. Therefore, a nested action cannot be lifted from the branches of an if. For an example of where this might be confusing, consider the following helper definitions that return data after announcing to the world that they have been executed. These definitions are intended to stand in for more complicated I/O code that might validate user input, read a database, or open a file. A program that prints 0 when number A is 5 or number B otherwise might be written as follows. Let's try it out. Yeah, and this is not allowed because it would be, I guess, equivalent to always executing both of these actions. This program would be equivalent to executing both actions and then doing this if thing, which kind of defeats the purpose, which runs getNum B regardless of whether the result of getNum A is equal to 5. To prevent this confusion, nested actions are not allowed in an if that is not itself a line in the do, and the following error message results. Invalid use. Okay, but they didn't really tell us how to fix it, and somehow also it is allowed to have, I guess this is in the condition, so it would also always be executed. But what if we want to do this? Then we need to get an IO nut here and do like pure 0 or otherwise getNum B, and then can we use arrow inside of string interpolation? That's actually interesting question, but it appears like we can. Yeah, we are only executing A and B is never executed, so yeah, if we do it like this, then it works. Flexible layouts for do. In Lean, do expressions are whitespace sensitive. Each I/O action or local binding in the do is expected to start on its own line, and they should all have the same indentation. Almost all uses of do should be written this way. In some rare contexts, however, manual control over whitespace and indentation may be necessary, or it may be convenient to have multiple small actions on a single line. In these cases, new lines can be replaced with a semicolon and indentation can be replaced with curly braces. Yeah, so here we have only whitespace sensitive layout, and if we use the curly braces here, then we have to use explicit semicolons and it's no longer whitespace sensitive. This version uses a semicolon to put two actions on the same line. Yeah, so that's also possible, I guess. Idiomatic Lean code uses curly braces with do very rarely. Running I/O actions with #eval. Lean's #eval command can be used to execute I/O actions rather than just evaluating them. Normally, adding a #eval command to a Lean file causes Lean to evaluate the provided expression, convert the resulting value to a string, and provide that string as a tooltip in the info window. Rather than failing because I/O actions can't be converted to strings, #eval executes them, carrying out their side effects. If the result of execution is the unit value, unit, then no result string is shown. But if it is a type that can be converted to a string, then Lean displays the resulting value. This means that given the prior definitions of countdown and run actions, we already saw we can execute it with #eval. This is the output produced by running the I/O action rather than some opaque representation of the action itself. In other words, for I/O actions, #eval both evaluates the provided expression and executes the resulting action value. Quickly testing I/O actions with #eval can be much more convenient than compiling and running whole programs. However, there are some limitations. For instance, reading from standard input simply returns empty input. Additionally, the I/O action is re-executed whenever Lean needs to update the diagnostic information that it provides to users, and this can happen at unpredictable times. An action that reads and writes files, for instance, may do so unexpectedly. Summary. Evaluation versus execution. Side effects are aspects of program execution that go beyond the evaluation of mathematical expressions, such as reading files, throwing exceptions, or triggering industrial machinery. While most languages allow side effects to occur during evaluation, Lean does not. Instead, Lean has a type called I/O that represents descriptions of programs that use side effects. These descriptions are then executed by the language's runtime system, which invokes the Lean expression evaluator to carry out specific computations. Values of type I/O alpha are called I/O actions. The simplest is pure, which returns its argument and has no actual side effects. I/O actions can also be understood as functions that take the whole world as an argument and return a new world in which the side effect has occurred. Behind the scenes, the I/O library ensures that the world is never duplicated, created, or destroyed. While this model of side effects cannot actually be implemented as the whole universe is too big to fit in memory, the real world can be represented by a token that is passed around through the program. An I/O action main is executed when the program starts. Main can have one of three types, either just unit for simple programs that cannot read their command line arguments and always return 0, or I/O of uint32 if you want to return success or failure, or a list of string to I/O of uint32 if you want to read command line arguments. Do notation. The Lean standard library provides a number of basic I/O actions that represent effects such as reading from and writing to files and interacting with standard input and standard output. These base I/O actions are composed into larger I/O actions using do notation, which is a built-in domain-specific language for writing descriptions of programs with side effects. A do expression contains a sequence of statements which may be expressions that represent I/O actions, ordinary local definitions with let and colon equals where the definition name refers to the value of the provided expression, or local definitions with let and an arrow where the defined name refers to the result of executing the value of the provided expression. I/O actions that are written with do are executed one statement at a time. Furthermore, if and match expressions that occur immediately under a do are implicitly considered to have their own do in each branch. Inside of a do expression, nested actions are expressions with a left arrow immediately under parentheses. The Lean compiler implicitly lifts them to the nearest enclosing do, which may be implicitly part of a branch of match or if expression, and gives them a unique name. This unique name then replaces the original side of the nested action. Compiling and running programs. A Lean program that consists of a single file with a main definition can be run using lean-run file. While this can be a nice way to get started with a simple program, most programs will eventually graduate to a multi-file project that should be compiled before running. Lean projects are organized into packages, which are collections of libraries and executables together with information about dependencies and a build configuration. Packages are described using Lake, a Lean build tool. Use Lake new to create a Lake package in a new directory, or Lake init to create one in the current directory. Lake package configuration is another domain-specific language. Use Lake build to build a project. Partiality. One consequence of following the mathematical model of expression evaluation is that every expression must have a value. This rules out both incomplete pattern matches that fail to cover all constructors of a data type and programs that fall into an infinite loop. Lean ensures that all match expressions cover all cases and that recursive functions are either structurally recursive or have an explicit proof of termination. However, some real programs require the possibility of looping infinitely because they handle potentially infinite data such as POSIX streams. Lean provides an escape hatch. Functions whose definition is marked partial are not required to terminate. This comes at a cost. Because types are a first-class part of the Lean language, functions can return types. Partial functions, however, are not evaluated during type checking, because an infinite loop in a function could cause the type checker to enter an infinite loop. Furthermore, mathematical proofs are unable to inspect the definitions of partial functions, which means that programs that use them are much less amenable to formal proof. Yeah, so I guess if we want to work with types as values, then we have to use total functions. Okay, this is the end of chapter 2.